start recording here. So we are being recorded. Okay, and we start out in differential equations with definitions and terminology. Now I'm going to pace myself so that you're able to copy the example down. This shouldn't say exercise, it should say example. Thought I fixed that, but we'll fix it now. And the examples, by the way, that I do, some of them are not in, I mean, the book has good examples, but I try to do sometimes different examples so you have a wider variety of examples to look at. So I'm going to pace myself, just like a face-to-face class. I was, assume you'd be taking notes and copying this example down. How many find it helpful to copy notes down to help them learn? How many find that helpful? Okay, Paige does, Christopher, Wajia, Thomas. Wow, a lot, Andre. Okay, a lot of you, and it is helpful. So let me give you a moment to copy this example down. Okay, so, all right. So you learned a little bit about differential equations in Calculus 2, in Math 182. You learned some different kinds of differential equations, like ones that would model exponential growth, for instance, and you learned about how to solve a differential equation if you can separate the variables. And that's sort of a starting point, good starting point for differential equations. Here we'll go into a much greater depth. But we start off simple. In this problem, we have a differential equation, and this is, does anybody know what model this is, this differential equation? dp dt equals p times 1 minus p. I don't know, you may have seen that in Calculus 2.
Population.
I'm sorry?
It's population. It's a population model.
Yeah, well, yeah, we sometimes call it a logistic model. But yeah,
Yes, logistic.
yeah, it has a carrying capacity. In other words, what you're doing is you're modeling the growth of a population with respect to time. That's dp dt, and that equals p times 1 minus p. Now, we don't know what the solution, well, we could find the solution of that differential equation because it's a separable differential equation. But what we're doing here is we're saying, here's a general solution, and p of t being equal to c1 times e to the t divided by 1 plus c1 e to the t. Okay, that's a general solution. because you have constants. The C1 is an unknown constant. We want to verify that that's a solution to the differential equation. Now, really, that kind of question is no different than saying this. If you had x plus 3 equals 7, x plus 3 equals 7, and then you were asked, hey, is x equals 4 a solution? Okay, how would you, I mean, let's say you didn't know how to do algebra, okay, and somebody said to you, hey, is x equals 4 a solution to that, to this equation here? How would you verify it? What would you have to do?
Well, you have to place the number 4 on the first equation. You substitute x by 4 with the 4, and then you add 3 plus 4, and everything that is on one side of the equation should be equal to the other side of the equation if it is a solution for that equation.
That's right, Thomas. That's right, and that's exactly right. And it turns out, of course, x equals 4 is a solution. So you verify it by showing that the proposed solution satisfies the equation. Well, we're going to do the same thing here. We're going to see if this P of t function satisfies the differential equation. So what do I have to do in order to check? What do I have to do with this population function P of t? Well, what's
Just
the
differentiate
upside?
function with respect to time.
That's right. We have to take that's right, Michael, and that's right, Matthew. We have to take the derivative with respect to t. So let's go to the next slide. And what I've done is I've done that. So, all right. So I'm doing dp dt. And what rule do we have to use when we take the derivative of this function? What's the rule that we're using? Okay, hopefully you're seeing it. Who's seeing, is this showing up okay? Who's seeing the page? You see text? A red circle, that's, okay, hang on one more.
Handwritten. Did you write? It's handwritten.
It's handwritten, yes, yes. That's right, Andrea. Okay, good. Quotient rule, that's right. So we know that the derivative of a quotient, the derivative of the quotient f over g is f prime times g minus f times g prime, all divided by g squared. And that's what I've done here. Okay, so hopefully, Christopher suggests Zachary refresh your page, but people are seeing this. Sometimes what you have to do, if you're using Google Chrome, you might have to clear out your cookies or clear out your cache, okay, under settings. How many maybe have done that before and it's helped them?
I am using Firefox and it works pretty well.
Firefox works well, Thomas? Okay.
Yep. So
I'm using Safari and it's fine.
Safari's good, okay. Okay, Andrea, very good. All right, well, Zachary, this is going to be recorded, what we're doing. So if Okay, so what I do is I use the quotient rule. And what I want, of course, on the right side of, what I want this whole, well, actually, let me go here. This here, after applying the quotient rule, and I know you know your derivatives rule, the question is, will that equal P times 1 minus P? Because that's what I have to show the right side equals. I have to show that dp dt, okay, dp dt, if this population function is a solution, then I have to show its derivative, dp dt equals P times 1 minus P. So what I do is I simplify the numerator, okay, by distributing the C1 e to the t to both terms here, and the C1 e to the t to both terms there. And then I get down to here, I get down to there, and something nice happens, doesn't it? Do you see something nice happening? Where did the 0 come in from? The parentheses. That comes from the derivative of 1, Paige. The derivative of 1 is 0. All right, no problem. Yeah, please ask questions. The only dumb question is the one not asked. Famous saying. So I'm wondering here, well, what nice thing happens here?
Well, you end up canceling two terms that are on the numerator, and you end up with one on the numerator.
That's exactly right, Thomas.
So it cleans
Those
your...
go out.
Yeah.
And so that gets us then C1 e to the t over 1 plus C1 over the quantity 1 plus C1 e to the t squared. So dp dt equals this. But the big question is, does this equal P times 1 minus P? All right, that's the big question. So we'll move to the next page, if that's okay. May I go to the next page? Everybody's comfortable? All right, very good. Then off we go. So, okay, now what I'm going to do is I'm going to write the fraction, this quotient, I'm going to write it this way. Why do I do that? Why do I do that? Well, because what's this equal to here? What's C1 e to the t over 1 plus C1 e to the t? What's that equal to?
That's P.
That's P. So all that's left to show is that this here equals 1 minus P. Well, all right. So we have to be a little bit clever here. I'm happy with the denominator, but the 1, what I'm going to do is write the 1 in an interesting way. I'm going to write the 1 as 1 plus C1 e to the t minus C1 e to the t. And then I can split the fraction as you see here. I can split the fraction as you see there. Now in WebAssign, they'll give you a little guidance for this kind of thing. You know, they'll break the problem down into steps, and they'll give you a little guidance. But sometimes you have to, you know, just have to be a little bit clever. And this here just equals 1. Well, the way Matthew, I broke down the right side is hold on here. This here, hold on. I want to just put this back. And all the markings I made will be in the recording. What I have to do is I have to write this as 1 minus p. Okay. Okay. So let's say this is like your first exam and you're turning in your work for a problem. Okay. You have to show me that you have 1 minus p. So what we do is we can write the 1. This is just like trial and error. You know, I thought about it. I tried a few things, and oh, this worked. 1 can be written as this way. And then I can split this fraction up like this. I mean, look at it this way. You can go from here to here, right? Because the denominators are the same on these two fractions, the difference of the two fractions, the denominators are the same. So you can go from, you can go this direction. Well, that means you can go this direction. And the reason I do that is because this will equal 1 then. That will equal 1. And I get my result. I get the result. And that shows that verifies that this population function P is a solution to that logistic differential equation. Okay. No problem. No problem. Are there any other good questions?
Yeah, I got a question.
Sure, Thomas.
So when you make the node 1 minus p, which that represents 1 minus p, and on the left side p on the blue line, blue writing, how can you? Yeah, no, not on the, but if you move up on the second line where you wrote the answers on the second step of the process.
You're looking here?
Yes. Can you explain? Can you explain a little bit more that, because I understand C prime e to the t over 1 plus C prime e to the t. I understand that.
I'll tell you. How did I come up with it, right? How did I come up with it?
Yeah, but mostly with the one on the second term, 1 over 1 plus C e to the t. If you could, please.
You mean this going from here?
Yes.
So you're going.
No, that one exactly. The second term that's multiplying. You know, yeah, that one. How can that be 1 minus p?
Well, okay, that's a good question. So I take the 1 and I rewrite it, and then I rewrite this fraction here like this. And voila, it works. I get 1 minus p here. I got 1 minus p. So I didn't just do this, like I had to think about this a little bit. It's like a little puzzle. But, you know, it worked. It worked. So there's no real, I'll tell you one thing. I know I needed to get a 1, right? I know
No,
I
I got it. I got it. No, I got it, Professor. I got it. Yes.
Okay.
Thank you. Thank you. Thank you.
Okay, you're welcome. All right, well then let's look at another example. I'm going to do 2 examples, and then hopefully you'll have some time to maybe start on your homework. But let's. Are there any questions before I move on? Thank you, Matthew. Thank you. All right, well then I will move on. Okay, hold on here. I want to go here. There's definitions, terminology. One thing that we need to understand is when a differential equation is linear in x. Well, what does it mean for a differential equation to be linear? Okay, what does it mean for a differential equation to be linear? So let me give you, and maybe I'll just comment on something here. While I'm at it, this just came to mind. Like, you know, how many have seen from Calculus 2 this differential equation, dy dx equals y? How many have seen that differential equation in Calculus 2? Or remember it? Does it ring a bell?
Yeah, I'm sure it's come up a few times.
All right, all right. Well, you know, so I can write dy dx equals y. That corresponds to exponential growth. That's an exponential growth model. But I can write dy dx equals y, that differential equation. It's a differential equation because there's a derivative in it. I can write dy dx equals y as dy equals y dx. Okay, I mean that is the same differential equation. And the reason I'm mentioning this is here I'm giving a equation that has differentials in it. You know, the dy is a differential, dx is a differential, but I can rewrite that as in the form of a differential equation that you're used to seeing. But I just want you to recognize that this here is a differential equation as well. It might seem a little strange. I don't want it to be strange to you. Okay, so let me give you a moment to copy this down. Okay, so linear differential equation. Linear differential equation. Okay, now let me just one moment here. what I'm doing is I'm going into the ebook here. So let me stop the sharing here and bring up the ebook. Okay, good, good. All right, so hold on here. Chapter 1, Introduction to Differential Equations. Okay. Okay, so they give some information. They give some information. But here in section 1.1, they talk about classification by linearity. Wait, hold on. Now, one moment. I got a lot of buttons open here. Is this okay? Good. It's showing. Good. Can everybody see the ebook? Okay. Is it showing up for you? Good. Good. Thank you, Thomas. Thank you, Kathia. So, in differential equations, there are two common types. There are linear differential equations and nonlinear differential equations. And the formal definition of a linear differential equation, okay, in Y is given right here. The differential equations have what are called orders to them, and they can be linear or nonlinear. So two important cases of a linear differential equation that they show here are given here. You have a first order differential equation on the left. This is in like where the number 7 is in parentheses. On the left, you have a first derivative in your differential equation. So it's a first order differential equation. On the right, you have using a second derivative. That's the highest derivative in the differential equation. So that's a second order differential equation. But they are linear differential equations because they match this form. They match this form. And you have to be very careful, and I'm going to go through this example, but in WebAssign, you have to be very careful with these kind of problems. You're going to have them for your first homework where the question will say, they'll give you a differential equation and they'll ask, is the differential equation linear or nonlinear? And you have one chance to get it right. And that's why I wanted to kind of, didn't want you to go into that homework assignment ahead of time and be talking about this. All right, but let's go back to the example here. Hold on here. Let me go back here. Okay, so what I'm going to do is I'm going to take my, no, that's the wrong problem. Hold on. Yeah, all right. I'm going to take my differential equation and try to rewrite it so it can match the form that is in the ebook. So first, well, here's what I'm going to do. First, I'm going to take the differential equation and I'm going to divide by the differential dx. Okay, I'm dividing every term by dx. Dx is it's a little value, right? It's a differential, so it's not equal to 0, but it's something, and so I can divide by that. It's non-zero, and so my differential equation that I started with can be rewritten this way. Okay. Now dx divided by dx is equal to 1, right? That equals 1. And so, I'm really showing a lot of good steps here. I get down to here. And what I'm going to do is I'm going to try to rewrite that differential equation. So the x times e to the x, I'm going to bring over to the right side. And then this term here, x times y, there's a y and a function x in front of it. And here's a y also. And what I'm going to do is I'm going to factor out the y from y plus xy. And that's what I did here. So now I'm in a position to determine if I have a differential equation that's linear with respect to y. And it turns out I do. Because these functions here, the coefficient function x in front of the first derivative, that's a function of x. The coefficient function 1 plus x in front of y, that's a function of x. X only. X only. And then on the right, x times e to the x, okay, x times e to the x, that's a function that's a function of x only as well. So this differential equation is what we say linear in y. It's a linear differential equation in y. Because we have dy dx, y is the dependent variable. When we say is the differential equation linear in the variable is our dependent variable. Okay. Are there any questions so far? Let me ask you this. Suppose that instead of dy dx, just suppose instead of just dy dx here, let me clear this out here. I'm going to ask this just, suppose instead of dy dx here, we had dy dx squared. Let's just suppose we had that. Would the differential equation be linear in y if we had dy dx squared? What do your instincts tell you?
I think it would, because the only thing no, not to y, but y square. No, it would not be.
Right, right. You can't, that's right. You can't have the derivative is not squared. You can't have that and have a linear differential equation. Okay, so what you have to do, again, you have to, when you're doing these problems, is the diffeq linear in the variable, you have to see if it can be written in the form that's given in the book. And you don't want to just jump and give an answer. You want to, let's now go to see if the differential equation is linear in x. Okay, so for that, what I'm going to do is, again, I start off with my original differential equation, but instead of dividing by dx, I divide by dy. I divide by dy. Because then I have dx dy. Well, Antonio, I think I am going through that. I am showing you that. But you might, this is one thing where, you know, if I were in the classroom, I could have the definition projected on the screen and then use a whiteboard, you know, but it's just, it might be helpful to have the classification of linearity. The definition comes after example 3 in section 1.1. So you may want to, if you want, have your ebook open. Well, again, that might be hard for you to do too, you know, because you're looking here. But let's go through this problem, and maybe you'll feel a little better. So what I do is I divide by dy, the differential equation by dy, and then this gives me a 1. And so the differential equation becomes this. And then I'm going to rewrite it so that my derivative term is first, and my x term is next. So the way the differential equation works is you always write it in descending order. You write it in descending order. Okay. It turns out here that you have here in front of dx dy, the coefficient function here is not a function of y only. Okay, in front of x you have the constant 1, but a constant is a function, and you can say, hey, the number 1 is a function of the variable y, you know, because like 1 equals 1 plus 0 times y. Okay, and so, hey, you know, 1 equals 1 plus 0 times y. Hey, 1 is a function of y. And then 0 can be thought of as a function of y also, because 0, you know, 0, you could think of it as 0 times y. So this almost worked. It almost worked, but the function is nonlinear in x, because the coefficient function in front of dx dy is not a function of y only. It's not a function of y only. Okay, so the book in example 4 has a nice example. Also. I wanted to do this one because, you know, it's one of the harder ones, but let me bring up the ebook, example 4. Are there any, I mean, I know this is going to take time to absorb, but are you, I mean, may I go to the ebook? Is anybody still copying here? Okay. Okay. Yeah, let's go to the ebook here. Okay, example 4, linear and nonlinear differential equations. They give examples. So you see here that, well, hold on. These three here. Hold on, can I highlight it, or am I gonna? Yeah. These three differential equations are linear because they match the form that's given in the book for a linear differential equation. The first one, you have to, well, you have to divide by dx to see it. But the second and third differential equations, if you can match that very nicely with the form of linearity given here in equation 6. But below these equations here, hold on. No, wait, yeah, did I lose it? Did I lose it? Is it not showing? Hold on. One moment. Okay, good, we're back. Here, in part B from example 4, these differential equations are nonlinear. So what you're going to have to do is basically compare the definition here to the form of the differential equation. There's really you have to develop a feel for this, and the only way to really develop a feel is to practice. So what I want to do, I want to stop there and give you a chance to work on that first assignment. So let me